Let's look at some AP examples of these fundamental theorem questions. This is a multiple choice question from one of the exams. It says a particle moves along the x-axis so that at any time greater than 0, its acceleration is given by this natural log function. If the velocity of the particle at 2, or is 2 at time equals 1, then the velocity of the particle at time 2 is what? All right, so we know to go from acceleration, which is given here, to velocity, which we're trying to find, uh, we would do the antiderivative. Maybe the hard part, or the part you could get frustrated by trying to attempt this problem, is that is not an easy antiderivative to find. And the reason they put that kind of hard looking function is they don't expect you to know how to do that antiderivative, and in fact you don't if you use your calculator to help you through this problem. What we got to realize to do this is that we can use that twist on fundamental to do this. If we did an integral from 1 to 2 of the acceleration, that would give us the velocity, which is the antiderivative, evaluated at 2 minus the velocity evaluated at 1. If we kind of change this, that means the velocity at 2 then should equal, if we add over the starting amount, the velocity at 1, our starting velocity, plus our change in our velocity, because remember, acceleration here, acceleration's the exact same as the derivative of velocity. And so antiderivative would give you the accumulation or the change in the velocity from 1 to 2. So now what we can do here is we know velocity at time of 1 is 2 plus, now what we're going to do to figure out this is just use our calculator here, because we know what this function ends up being. It's natural log of 1 plus 2 to the t dt. So this part we're going to use our calculator to figure out, and then we should be able to come up with the answer. So on the calculator, we'll use our integral function here by selecting math. Select our integral, definite integral. We're going from 1 up to 2. Type in this natural log function. And then make sure you get your last variable in this part. We'll forget to close the parentheses here. And now hit enter, and it gives us, it should give us the change. So from 1 to 2, the velocity increased by 1.346. So if we add that with the starting velocity of 2, it gives us the total here of 3.346 for the overall velocity, and we can see E there was the correct answer then to this problem. All right, let's look at another AP question. This one's a free response. This was a no calculator question. So there's a graph shown here. It says let f be a function on this closed interval from -3 to 4. F0 equals 3. The graph of f prime and the derivative of f consists of one line segment and as a semicircle shown. And you can see that this function is continuous here. On what intervals, if any, for part A, is f increasing? Justify your answer. Well, this is f increasing. F would be increasing anywhere that the derivative is positive or bigger than 0. So you got to be careful on this one. We're not like looking literally at slope here to do this, because this is already the graph of f prime. And so what we want is, if this is the graph of f prime, we're looking where is this graph, like literally positive here. The only place where we have this graph being positive is right in this region. And so for part A here, we would say that f is increasing on the interval from -3 to -2. So that would be where it is, and the justification is what we had over here, because on that interval f prime is positive, greater than 0. All right, let's look at part B. It's the same question. Find the x coordinate of each point of inflection of the graph of f on the open interval from -3 to 4, and again, justify your answer. Okay, so we know inflection points, those happen where the second derivative is equal to 0, and you got to make sure not just it's equal to 0, but and that the sign changes from either positive to negative or negative to positive. Okay, so on our graph, if this is again the graph of f prime, where is the second derivative going to equal 0? Well, that would happen anytime there's a change in slope here of this graph, from either going from decreasing to increasing or increasing to decreasing. So the two places where this changes from increasing to decreasing or decreasing to increasing would be at -2, x equals 0, and at x equals 2. You can see here it changes from decreasing to increasing, and then here it changes from increasing to decreasing. So the answer that we would say here at x equals 0, that's a inflection point, because the derivative of f changes from decreasing to increasing. And then also another inflection point here for part B would be x equals 2, and that's because the derivative changes from increasing to decreasing. All right, let's keep going here. Part C, find an equation for the line tangent to the graph of f at the point 0,3. Now, remember, this is not the graph of f here. This is the graph of f prime. So what we know is we have this point right here, 0,3, that we're using. They also give it to us up here. If we're going to come up with the tangent line equation, we can use like point slope here. But we do need that slope. We have the point. We know our y value is 3 here. We know our x value is 0. The only thing we don't know is that slope. Well, how do we find slope? Derivative. So what we need on this is, what is the derivative at the location we're doing? We're trying to find what's the derivative at 0 going to equal. Well, we can get that from this graph. At 0, if we follow our graph here, looks like the slope is -2. And so that would be the slope that we would want right here. There's no need to simplify this. They didn't ask for it in slope-intercept form. You would be good just keeping your answer like that. All right, final part to this one, D. Find f of -3 and f at 4. Show the work that leads to your answer. Okay, so here, this last part, this is where that kind of twist on the fundamental theorem is going to happen here. We know if we did the integral of, and our 1 point we know is 0, 3 here. So if we did the integral from -3 to 0 of the derivative of f of x, which is our graph over here, remember this is the graph of the derivative, that would equal the antiderivative of this, which is, if we start with the derivative, the antiderivative is just our function evaluated at 0 minus our function evaluated at -3. So if we want to find f at -3 here, we could manipulate this equation around, and it looks like if we would add that over, that would be equal to now f of 0. F of 0, we know that's going to be equal to 3 here. So I think what we're going to do next, let's subtract that. So f at -3 then would be equal to our starting value, f of 0 minus the change that happens from 0 to, or -3 to 0. F of 0, like we said, is 3 up here, so we can plug that in. The integral we're going to have to figure out geometrically by looking at the picture up there. So from -3 right here to 0, what's the change going to, or what's that area going to be? Well, right here, that area is just area of a triangle, a 1 by 1 triangle, so half of base times height. So that area is 0.5 or 1/2. Plus, what else do we have? So now we got another triangle right here. That one's a 2 by 2 triangle, so half of 2 by 2, or 2 times 2 is 4, half of that would be 2, but it is underneath, so that's going to come out to be -2. So now if we just finish simplifying this, that should lead to our solution for f of -3 here. We got 3, half plus -2 is -1.5. If we're adding a negative, that would equal 4.5. Why don't you kind of try the next one, see if you can find f of 4. So pause the video. It's very similar manner. See if you can solve for that one. All right, let's see what you got. Here, if we did an integral from 0, the value we know, to 4 of the derivative here, that should equal antiderivative, which is our function at 4 minus function at 0. What we know here now is if we want to find f at 4 here, if we add over our starting amount, should be f of 0 plus our change. We know f of 0 again is 3. Our change, you're going to have to use some geometry again. From 0 to 4 is right here. There's a semicircle involved. You got to be a little bit careful now. We're looking for this area, which is a little bit harder to find. You almost have to think like there's a rectangle here and then subtract that semicircle. So using geometry, that's a 2 by 4 rectangle, which would be 8, minus the area of the semicircle would give us this area we're looking for here. So that's a area of that semicircle. The radius is 2 here. Area of a circle is pi r squared, so it'd be pi times 2 squared, but it's a semicircle, so divided by 2. That would give us the area we're looking for. If we simplify this, now we got 3 plus 8 minus 2 squared is 4, divided by 2 would be 2, so 2 pi. Combining together, we get 11. Oh, sorry. Screw that up here. One other thing we got to forget, or I forgot here, this is underneath the x-axis, so we want to make sure this whole thing ends up being negative. So we would have to make sure that we put a negative in front of this, so it's going to end up being minus everything we get in there. So 3 minus 8 minus 2 pi, which is a little tricky here. So you almost got to distribute that negative sign. And the final answer would come out to be negative 5 plus 2 pi. So that should have been the final result there.